Hello class, welcome to Geometry Lesson 11.3, Pyramids and Cones. So our essential question for today is, how are the volumes of pyramids and cones alike? And our goal is to use the properties of right and oblique pyramids and cones to calculate their volumes and surface areas. And again, finally, we're going to look at volumes, but we're also going to take a look at surface areas. So we'll add that question there as well. How can the surface area of a pyramid or cone be calculated? All right, so let's take a look at, let's review Capillarys Principle. Recall from the previous lesson that Capillarys Principle was based on the fact that if you have two or more solids and you want to compare their volumes and they have the same heights, so the solids have the same heights. So in this case, let's assume maybe that this has the same height as this, right? And you were to make slices at each level. Slice here, and if you were to look at the areas of the cross sections from those slices and the areas are the same, then that must mean that the volumes of the two are the same, two solids in question. So if I take this first slice right here, I can see, well, I just have this small circle there, and it's the same for both of them, right? It's a small cylindrical disc kind of thing. And here, if I take this slice here, it's the same dimensions, circle there, circle there. So notice that the dimensions are the same at each slice. At each slice, the areas of the cross sections are the same. At the bottom, that's where the circles are largest, right? But it's still the same area, and they have the same height, and therefore the volumes of these two pyramids must be the same. So that was Capillarys Principle. Even though these are, now if you look at the ones on the bottom, you're looking at a cone and a pyramid, right? So for the cone, if this circle right here has the same area as the square, which is possible that they could have the same area, right? The area of a circle is pi r squared, and the area of a square is just base times height, right? Now if the, let's assume, yeah, so let's right here, the area of this is base times height, and the area of circle on the left is pi r squared. Now, if the dimensions of the, let's say the square here is, for example, or this rectangle or whatever, is pi, and this height is 1, for instance, right? Then the area of this rectangle is pi times 1, which is pi. And let's assume that the radius of this circle is 1. So then the pi r squared would also be pi, right? So in that case, the area of the circle is the same as the area of the square, or the rectangle rather. And therefore, Capillarys Principle would apply here, and the volumes will be the same. So volumes equal in this case, right? Assuming that they have the same height. So Capillarys Principle applies to different cross-sectional shapes as well, as long as they have the same area. All right, so the volume of a pyramid and cone. So let's talk about how we would derive or come up with an idea of what the volume of a pyramid or cone could look like. Now we have here a square prism or a cube, and in this case, for this cube, we can think of it as being broken into 3 pyramids. So we have this pyramid given in blue. Notice that that's an oblique pyramid because it's a little bit angled, right? It's not a normal pyramid. It's not a right pyramid, it's more angled like this. And it's a square pyramid, but it's just angled like that. And notice that I can form 3 of those. This one right here, and then this one right here could be considered to be 3, right? And then you can kind of picture the other one. It's so we have 1 here, we have 2, and then we could form another one kind of like that, right? By this shape here, we can conceive of another one on that side. So there's actually 3 pyramids that can be formed and fit in a prism. And therefore, we know that the volume of a prism is B equals BH. And so if we know that 3 pyramids fit into a prism, that means that each pyramid is exactly 1/3 the volume of a prism. And therefore, the volume of a pyramid is 1/3 the volume of a prism, which is, the prism is BH, so it's 1/3 BH. Now for cones, this is actually harder to visualize, right? It's kind of hard to visualize 3 cones fitting into a cylinder. And so what we do is we usually use Capillarys Principle. We know from earlier that if I have a prism and I have a cone of the same dimensions, right, the same cross-sectional area, and if they have the same height, then that must mean that the volume of the cone and the pyramid must be the same volume. So we can use Capillarys Principle to help us here. For cones by Capillarys Principle, a cone could have the same volume as a pyramid, and therefore also would have 1/3 the volume of a cone rather than a prism. So we can apply the Capillarys Principle to apply this instance from a cone to a cylinder. So let's go ahead and take a look at this. The volume of a cone is 1/3 VH, or 1/3 pi r squared h. So if I look at this animation here, we can have 3 cones. So that's 1 cone. There's a second cone. If we were to melt that down, right, or fill up the water that's in that, there would be 3 cones that would fit in that cylinder. Okay, so now we got the volume for the cone and the volume for any pyramid. So let's take a look at the first question. First question is an oblique cone, right? However, it doesn't matter if it's oblique or not. By Capillarys Principle, this is the same as a regular cone in terms of volume. So the volume of this cone is 1/3 pi r squared h, which is what we mentioned earlier. So it's going to be 1/3. So let's write that volume there, and then we have the volume here. We have 1/3 pi times. Now the diameter is 6, right? That's the diameter, so the radius has to be 3, half of that, times the height is 7. All right, so we got 3 squared is 9. 9 divided by 3 is 3. So this becomes just 3. And then 3 times 7 is 21. So this is 21 pi. All right, so now let's look at the volume of the pyramid for part B. So for part B, we know that it's 1/3 times the base area. So let's find that. The base is a rectangle, so it's 9 times 7, base times height. So it's 9 times 7 is your base area, and then times the height of the pyramid, which is 6. So there's your formula. Now we know that 9 divided by 3 is 3, and then 3 times 7 is 21. 21 times 6 is 126. And that's going to be in centimeters cubed. All right, so now let's take a look at this oblique pyramid, and it's not only an oblique pyramid, but it's a hexagonal. It's an oblique hexagonal pyramid. So we have hexagon here. Okay, so let's go ahead and show you how to do that again. Remember that the volume of a pyramid is 1/3 base area times height. So we need to figure out the base area for this hexagon. Again, we did this earlier in the previous lesson, where if we knew that each of the dimensions here is 2, so I can conceivably make 6 of these triangles here. So I'm going to find one of these triangles and then find the area. All right, so we know that this dimension is 2. So again, we can break this up into 2 right triangles. We know that, and then so it's going to be a 30, 60, 90 triangle. So this is 30, and this here is 60 degrees. So we got a 30, 60, 90 triangle. Let's go ahead and draw it out a little bit bigger. And if that's 2, then remember, for any 30, 60, 90 triangle, the dimensions, the way it's set up, and actually this is actually reversed. This is actually supposed to be 30 down here. So let me correct that. This is supposed to be 60 up here and 30 on the bottom, because here, let me draw this a little bit larger. This is a little bit too small here. So for this hexagon, we know that the angles in any hexagon is 120 degrees, the interior angles. Now, even if you didn't know that, that's okay, because you could figure it out. If you have 6 triangles here that fit, 1, 2, 3, 4, 5, 6 triangles, and a full circle is 360, then this angle has to be 60 degrees, because 360 divided by 6 triangles is 60 degrees. And if I split this up into 2 right triangles, then this has to be, it can't be 60 anymore, right? Each of these angles is 30 degrees. And then because this is a right triangle, it's a 30, 60, 90 triangle. All the angles have to add up to 180 in a triangle. So we got our 30, 60, 90 triangle. And now instead of this entire thing being 2, it's going to be 1, cut in half. All right, so now we got our right triangle. Now we know that for any 30, 60, 90 triangle, the dimensions are x square root of 3, and 2x. So if I know the shortest side, I can double it to get the hypotenuse. So if this is 1, then this is 2. And if this is 1, this is 1 square root of 3. All right, so now I know the dimensions of that triangle. So the area of that triangle is 1/2 times base, which is the base of this triangle. The big triangle is now 2, and the height is 1 square root of 3. And that's the area of this big triangle. And so half of 2 is 1, so the area is just square root of 3. All right, so the area of that one triangle is square root of 3, which means that the base area is 6 square root of 3, 6 of those triangles. Okay, so we have 1/3, 6 square root of 3 for those 6 triangles times the height, which is 5 meters. And so the total volume of this oblique hexagonal pyramid, 1/3 of 6 is 2. 6 divided by 3 is 2. And then 2 times 5 is 10. So it's 10 square root of 5 meters cubed. All right, so let's take a look at the surface area of a cone. So we have a right cone on the bottom. In order to find the surface area of this cone, well, we know that we have a circular base here. So let's go ahead and so we know we have a circular base, and we know that the area of that circle is pi times r squared. So that part is straightforward. Now, in order to find the part that wraps around the cone, we need to understand how a cone is constructed. So the way I would construct a cone like this is I would take a large circular piece of paper, and I would cut out I would cut out a sector. Okay, so I would cut out a sector of that circle. And this sector right here, which is given in red, is the entire area of this sector is actually the part that wraps around the cone. So this sector given in red is actually this part of the cone that wraps around. It's actually that entire surface area. And so that's how you would construct this cone, is you would cut out a sector of a circle and you would wrap it around to make the cone. So it turns out that the arc length of this sector is actually the circumference of the base of the cone, because this sector right here, this cutout of the sector, actually wraps around itself to make the cone, and the radius of that cone we'll call r. And so that means that the length of that arc has to be equal to the circumference of the base of the cone. So now we know that the arc length of that is 2 pi r. Now, in order to find the area of this sector, so we're going to call it A, we need to know the arc length, which we now know. So what we're going to do is we're going to take the ratio of the arc length of this sector to the arc length of the entire circle. Now the entire circle is 2 pi times the radius of that circle. So we're going to say that the radius of that circle is L, script L. And L, turns out that L is actually the slant height of the cone itself. So this slant height is actually the radius of this larger circle of which we cut out earlier. Okay, so the area of this large piece of circular paper before we cut it out is pi L squared. All right, so in order to derive the formula, we need to know the area of the part that wraps around the cone, which is this red sector. But the ratio of that area to the area of the entire circle, which is pi L squared, is equal to the ratio of the arc length of that sector to the arc length of the entire circle, which is the circumference. The circumference of the large circle is 2 pi L. And notice that the 2 pi's cancel out, And we know that one of these L's actually cancels out. So if I were to take this and move it over, one of these L's cancels out. And then I can multiply by pi L on both sides. And I get the area, the surface area of the part that wraps around the cone, which is pi r L. And there's our derivation for the surface area of the cone that wraps around. It's the area of the bottom, which is pi r squared, plus the area of the part that wraps around the cone, pi r L. And here is the the surface area of a right cone as we derived it, pi r squared plus pi r L, where L is the slant height of the cone. All right, so let's take a look at the surface area of oblique cones. This is a little bit more complicated because you have two slant heights for an oblique cone, right? We'll call them L1 and L2. So since a cone, so we know that any cone has the circular base and the face that wraps around it. So for the oblique cone, we have the circle, which is pi r squared. But it turns out in order to find the surface area of the part that wraps around the oblique cone, because you have two slant heights, you need to find the average slant height. So it turns out that the surface area of an oblique cone is the pi r squared plus pi r average slant height. And so the L is not just L, it's the average L. And so you have to add up the two slant heights divided by 2. And that's how you would find the surface area of the oblique cone. Okay, so let's go ahead and find the surface area of a pyramid. Now pyramids are a little bit more complex because you have a slant height of the pyramid, right? This L is a slant height, and usually they give you the height of the pyramid, capital H. And so if I wanted to do the surface area of this pyramid, well, I need to do I know that for this pyramid, it has the one base and in the triangular faces. And the surface area is the sum of the base and the triangles. But remember that the area of the triangles is 1/2 base times the slant height. If I wanted to get the area of this triangle here, I need to know this L, right? That L is the actual height of that triangle. And so I need to figure out the L, and if the triangles are all different in the pyramid, then you need to find all of the slant heights and then add them together for the areas of the triangles. And then you can find the slant height usually by the Pythagorean theorem. For most pyramids, you can do that. So let's take a look at an example for the surface area of the cone. This is just a regular cone. We're not going to be looking at oblique cones really. I gave you the formula, but we're not really focusing on it. So let's go ahead and get the surface area. We know the surface area of a cone is pi r squared plus pi r L. Now the radius of the cone is 7. And we got 7 for the radius again. And then we need L. So L is the slant height. So I need to do a Pythagorean theorem in order to get the slant height. So we got a right angle here, and we need to find L. So the L is the hypotenuse here. So we got a squared plus b squared equals L squared. So 7 squared plus 21 squared equals L squared. And we go ahead and do the math there. So we got to do the square root of both sides to get rid of the L, to get rid of the square root in the L. So we got 7 squared, which is 49. We got 21 squared, which is 441. So we add those together, we get 490. Then we'll take the square root of 490, and we're going to get a decimal, and we get about 22.1 approximately. All right, so now we know that L is 22.1. We can plug it in there and get the surface area for the cone. So we got surface area is 49, so 7 squared is 49, so we got 49 times pi, and then we got 7 times 22.1, which is 88.4. 88.4 plus 49 is 137.4. So it's 137.4 pi. And of course, you can get it as a full-on decimal by replacing pi with 3.14 to get the actual surface area. All right, so for part B, we want to find the surface area of this pyramid. So we got a rectangle. So this rectangle is... All right, so let's go ahead and we're going to go ahead and make ourselves some room for the second problem here. So for part B, we have the rectangle base, which is 7 times 4. So the surface area is 7 times 4 plus. Now we're going to do the triangles. So let's look at the triangle piece here. So if I wanted to get this triangle, well, I'm going to need this slant height right here. So I'm going to need this slant height here. Now I know that this base of this triangle, this right triangle, is half of 7 because this is the side that it's based off of. So this is actually 3.5 because it's half of the 7. And we know that this height of this is 7. And so we can figure out this L, we'll call this L1. That'll give us a slant height of that triangle. Okay, so we're going to use Pythagorean theorem. So we got 7 squared plus 3.5 squared is equal to L1 squared. All right, and then we're going to take the square root of both sides to get the slant height. And the slant height is, let's see here, we got square root of 49 plus 3.5 squared. You get 7.83. All right, so now we got the slant height there. So that's 7.83. So now the area of this triangle, the one on the right, is 1/2 times base, which is 4. The base is 4, times the slant height, which is 7.83. Now there's 2 of these triangles, one on the right and one on the left. So I'm going to go ahead and double it and take care of those 2 triangles. So now we got 2 more triangles. The one on the front and the one in the back. So I'm going to say that there's 2 of them. 1/2 times the base. So the base of that triangle is 7. And we're going to find the slant height. So let's focus on doing that. So this is going to be this slant height. We'll call this L2. So again, we're going to construct a right triangle like we did earlier. This side is half of 4. So it's going to be 2. And so we got 2 and then 7, so we can take the square root of 2 squared plus 7 squared. So L2 is the square root of 2 squared plus 7 squared. And so we got the square root of 4 plus 49, which is 7.28. So we can plug that in for the height here, and we get our final surface area. So we got 7 times 4 is 28. Then we got here all of this for this first triangle, which is, and so we'll add up all these together and see what we get. And we get a total surface area of about 110.28. All right, and that's how you would do it for a cone and for a pyramid. Pyramid's a little more complicated because you're having to find the slant heights and all that. All right, I hope you learned something from this video, guys. Take care. Thank you for watching this. And as usual, I'll see you in the next one.